Okay, this is a re-recording of my video on Chapter 7, which is on simulations. So I'm going to just basically recap what we talked about in class the other day. So the first thing I want to talk a little bit about is on independence. Just as a reminder, we talked a little bit about independence previously. So if you were to take a coin and flip it, the number of heads is going to be independent of tails. The coin doesn't remember anything. And so a lot of times we can do a simulation when we want to do more difficult probabilities than that, although we'll use that. Our first simulation will be to simulate a bunch of coin flips. Sometimes it's a lot easier to do that mathematically. So another word for independence is memoryless. As I mentioned before, the coin has no memory. Whereas maybe a deck of cards, if you pulled a king out of a deck of cards, that might be, you could think of the deck of cards would remember that the king was missing, and so another king would be less likely, or even any other cards. The probabilities will change because the deck of cards kind of remembers what cards were in there. So once again, event E is independent of F if E has no impact on F and vice versa. So another example would be dependence, and I'm sure that I'm asking the class something about independence and dependence for a moment here. So, okay, so the first thing that you need to do when you're working on a simulation is you need to create some sort of a legend. So if we're using the random number table in the book, you know, it's got a bunch of numbers 0 through 9. So we have to decide, how do we decide if you know, a 0 is a head or a 1 is a tail or whatever, you know, how can we use this random number table? So there's lots of different ways to do this, and the first thing I think I'm going to do is I'm going to share my random number table here, maybe. Okay, so one way we could do this is to do odds would be heads and evens would be tails. Now that's not the only way to do this. One of the things you'll find with simulations is there are lots of ways to do this. And I'm sure that I'm asking the class now, what's another way to do this? Another way to do this would be, I could maybe number 0 through 4 are heads and 5 through 9 are tails. Since those are evenly distributed, that's not a problem. So another way to do this using Microsoft Excel is we could just do random numbers between 0 and 1. And we could say that 1 equals heads and 0 equals tails, for example. Now the advantage to doing that is you can just add up the number of heads, and then you'll have your number of heads. It's very easy. It's just a simple sum, ones and zeros. So that can be another way to do simulation of 100 or 1,000 flips. So that can be very useful in Excel. Not as useful with the random number table generator. Now, what I'd like to do is I'd line group 1 to be coins, group 2 to use the random number table, group 3 is going to use line 3 of the random, or row 3 of the random number table, using the legend 0 through 4 for heads and 5 through 9 for tails. And then group 4 is going to use Excel. So they could do the ones and zeros. So there's lots of ways to do this. Once again, group 1 is going to just flip the coin 100 times. Group 2 is going to use the random number table, and they'll use odds for heads and evens for tails. Group 3 is going to do 0 through 4 are heads and 5 through 9 are tails. And then Group 4 will do the Microsoft Excel, and they'll just use ones and zeros. So once again, that command is rand between 0 and 1. Okay. I think I was trying to share the results of our experiment. Now obviously 100 wasn't too bad, but if you wanted to flip the coin 1,000 times, you're probably going to want to use Excel. That's probably going to be the fastest way to do this random number generator thing. So, okay, so another way to do this, let's pretend that we had 70% employment and 30% unemployment. So you saw that I just scratched out the odds and evens will no longer work, because now we're not talking about 50-50 heads, we're talking about 70-30 heads. So odds and evens won't work, neither will the legend 0 through 4 and 5 through 9, neither will the Excel method ones are heads and zeros are tails. So we're going to simulate 30% unemployment, which is 70% employment, and we've got to figure out a new legend, either using the random number table or using Excel. We'll talk a little bit about both of those in just a minute here. How would you define a group of 70% employed and 30% unemployed? So we can continue to do so with the table, but in this case, since 70% is a nice round number, if I were using Excel, I could go 1 through 7 would be employed, and then 8, 9, and 10 would be unemployed. However, if I'm using the random number table, I don't want to use 2 digits, and 10 is a 2-digit numbers. So a different way to do that, as opposed to using the odds and evens or the 0 through 4 and 5 through 9, is I could say 0 through 6 are employed and 7 through 9 are unemployed. Or, as I wrote on the board here, I can also do it the other direction. 1, 2, and 3 are the unemployed, and then 4 through 10 would be employed. So once again, there are lots of ways to do this. Now that's a great way to do it in Excel. It doesn't work so well with the random number table. So using the random number table, I could do 0 through 2 are unemployed and 3 through 9 are employed. Now the nice thing about that is I can still use single digits. 0, 1, and 2, those are 3 numbers. So make sure you count, so sometimes people don't count the 0, but 0, 1, and 2 are 3 numbers, so that would represent 30%. And then 3, 4, 5, 6, 7, 8, 9, that's 7 numbers. Okay, if you include the 3 and the 9, that counts to 7. You might want to do that with your fingers to make sure you're there. And so that would work. Now, if I wanted to use 2 digits, I could use 0, 1 through 30 are the unemployed, and I could use 31 through 100 as employed. Now that's probably a great method that you're going to use for Excel. If you're using the table, you probably want to decrease all of those values by 1. So you could go 0, 0 through 29 would be unemployed, and 30 through 99 would be employed. So once again, there are almost an infinite number of ways to do this. There are correctly, and there are also an infinite number of ways to do it wrong. So these are lots of different examples. It does make your tests kind of interesting to correct, because there is no one way to do it. And now I'm writing what I just mentioned there in a second. 0 to 6. Oh, so 0 to 69 would be employed, and 70 through 99 would be unemployed. That would be another method. Okay. So the important thing when you're doing your test is you've got to define your legend. I've given you here actually 4 on the board, plus I gave you another one. 5 ways to do this correctly, and of course there are lots of ways to do it wrong as well. So we can do that. So one of the things I will just mention on the test once again, just to reiterate, the most important thing when you're doing a simulation is to tell me the legend, how you are defining your simulation, and then I can follow what you did and see if you did it. Now, let's do another simulation similar to the one that we just did, but this time I want 73% employment and 27% unemployment. So therefore I can't use single digits anymore. That's why I've X'd out those. So no longer can I use a single digit because now I've got 73 and 27. So I have to use a minimum of 2 digits for my simulation. So how could we do that? So one way that we could do that if we're using Microsoft Excel is we can go, when we're creating our legend, trying to read the board here, and it's very fuzzy, I apologize. 00 through 76. Oh, except for that should say, I think I wrote the wrong thing on the board there. That should say 72, and then oh, I can't read it. 00 through 26. That's what it says. Okay, so 00 through 26 would be the unemployed. 27 through 99 would be the employed. So that would work well with the random number table. And then if I was using Excel, I could number it from, say, 1 to 73 if I wanted to define the employment first. So that's one possible way with the table, as I wrote there on the board that says table. And then if I'm doing it in Excel, I believe I'm going to write here 1 through 73. And those would be the people that are employed. And 74 through 100 would be the unemployed. So once again, lots of ways to define this. These are just one of many ways to do this correctly. It would be inappropriate, though, to go from 0 to 73 because that would actually be 74, because if you count the 0, that adds another one on there. So make sure when you're doing it, 1 through 73 and 74 through 100 would be a good way to do that. Now, boy, this camera isn't very good. I'm saying do a simulation of 100 people. And so you could, I think I broke people up into groups. If you hadn't used the Excel portion, I wanted you to use Excel, and if you hadn't used the table, then I wanted you to use the table. So we'll take a break, and that was our classroom activity that we did right there. Okay, so now what we're going to talk about is tree diagrams. These can be very useful for dependent probabilities. Up to now we've been talking about independent simulations. We're going to talk about some dependent events as well in this section, and so the tree diagram can work very well, especially for dependent events. So just as a reminder, we talked a little bit about the deck of cards. I'm going to give you a scenario. And hopefully this never happens to you, but let's say that you go to the doctor and the doctor tells you that you need a new kidney. Now this would be a terrible thing to learn, but the doctor says, okay, so here's some information you need to know when you're getting a new kidney. So first of all, 90% of people who have surgery to get a new kidney survive surgery, but 10% die. Now, obviously, those are pretty good odds, but you could be in the 10%. And we'll feel bad if you didn't survive surgery, but mathematically we wouldn't care about you anymore. And so then we'll move on to the next step. Now, remember that just because you have a new kidney doesn't mean your body will accept it. And so the doctor tells you following surgery, 70% of patients, the new kidney works. Actually, it wasn't 70%, it was 60%. 60% succeed with the new kidney, and 40% have to return to dialysis because the body rejects the kidney and it doesn't function any better. So after that step, one of the things that happens is we want to know how long people live. If they live 5 years. And so the doctor tells you that 70% of people who have the new kidney live 5 years, but just 50% of people live 5 years that are back on dialysis. So you can see that kind of depends on the previous step. Now, one of the questions I always love to ask is, you probably want to know, what is the probability that you live 5 years? Now, as we look back at these things, notice the 90 and the 10 adds up to 100%, the 60 and the 40 adds up to 100%, but the 70 and the 50 do not add up to 100%. Now, so, we talk about independence. The coin flip would be independent, and the deck of cards would be dependent. But as we look at the 70 and the 50, okay, are those dependent on each other? No, we can see that those add up to 120%, so that's a problem. So they're not independent, but they're not dependent on each other either. So there's a third option, which means they're not independent of each other. They're dependent on some of those previous steps. So you've got independence, dependence, and then not independence, which is neither independent nor dependent. So that can be a little confusing for people, but just remember that 70% depends on the 60% and the 50% depends on the 40%. So they're dependent on other things, but they're not dependent on each other. So those two events are not independent of each other. Okay? And in fact, they are dependent on previous steps. So anyway, just wanted to emphasize that. All right, so now let's go ahead and we're going to create a tree diagram here. And I know I didn't give myself enough room on the board. I probably should have given myself more room. But let's say, your first step is to do surgery. Okay, there are two options here, and so I'm going to just draw two branches. You're either going to live or you're going to die. Okay, now we can put the probabilities in here that the doctor gave to us. The probability that they live is 90%, or 0.9. I'll write that as a decimal. And the probability you die is 0.10, or 0.1. Okay. Now, once you survive surgery, you've also got two options. Either the new kidney will succeed, or you will have to return to dialysis. It will fail, and you will return to dialysis. So we can add those probabilities in there as well. So you've got 0.6 that it succeeds, or 60%, and 0.4, or 40% that it does not succeed. Okay? So now we've got two more options, and I will branch those up high because I didn't have enough room on the board. Should have given myself more room. Okay, so the two options to succeed are to live 5 years or to die. And we know that to live 5 years with the new kidney that has succeeded is 0.7, and then we can use the complement rule to say what's the probability you die? 0.3. Okay? We can do the same thing if the patient has to return back to dialysis. They're either going to live 5 years or they're going to die. And so we can write those probabilities in there as well. And the probability that they live 5 years is 0.5, and the probability that they die is also 0.5. That one's actually kind of a coin flip there. Okay? All right, so now as we're doing this, we can figure out the theoretical, and we could also do a simulation to try to do this. Now we'd probably, if we wanted to do this accurately, we'd probably want to do 1,000 simulations, but I don't want to make you guys do that many. All right, so the theoretical thing is, you could live through surgery, it will work, and so we're going to multiply those three probabilities together that I just circled, 0.9 times 0.6 times 0.7. I believe that equals 0.378. Now the other option to get to 5 years is you survive the surgery, it does not work, but you still live 5 years. Okay, so now I'm going to multiply those three that I highlighted in purple, 0.9 times 0.4 times 0.5. Okay, so that value, I believe, equals 0.18. Now, since there's two ways to do those, I can add them together, and I didn't write that on the board, but you can see it's 0.558. It's just off the board. I need a cameraman to aim my camera and keep it focused a little bit better. So, all right, so that would be the theoretical probability. Now, the interesting thing is you look at that 0.558 is, it's only a 50% probability that you live 5 years on dialysis anyway, so you haven't really improved your probability that much. However, obviously, you know, you don't have to go into dialysis, or you have a chance of not going into dialysis, 0.378. So in my mind, that would be worth it to me to go ahead and not have to do dialysis and get the kidney transplant. So, all right, I believe I'm just recapping here. Okay, so now let's talk a little bit about how we would do a simulation based on these dependent probabilities. So we've got to come up with a new legend, and our first legend is going to say, okay, did you survive surgery? And so what you could say is 0 means you die, and 1 through 9 means you live. Now that would work very well with the table, since these are nice round, 10%. We can use a single digit for these. We could do it with 2 digits as well, but a single digit will work just fine. Now on step 2, we need to figure out what happens with the next part of our thing here. And so we've got to decide if the transplant succeeds or if it fails. So one legend that we could come up with is 0 through 5 is a succeed, and 6 through 9 is a failure and back to dialysis. Now remember, 0 through 5 is actually 6 numbers. So use your fingers, 0, 1, 2, 3, 4, 5, that's 6 numbers. Okay. 6 through 9 is 4 numbers, 6, 7, 8, 9, that's 4 numbers, so that's 40%. And then finally, the last step, I can't read what I wrote on the board there, but we've got 2 options here. We could say 0 through 6 is live 5 years, and 7 through 9 is die. Or if we're on the other part, we could say odds mean you live 5 years and evens mean you die. So sorry that cut off the board. You guys need to let me know if you can't see that on the recording, but I believe that's what I wrote on the board, or at least even if I didn't, that would work just fine. So all right, so at this point I said go ahead and I want you to simulate 10 patients, and we want to see if, theoretically you should get around 5. Now the way you're going to have to do this is you're going to need 3 single-digit numbers per patient. Okay, so you're going to need a number for whether they survive surgery, 0 through 9, a number for whether the thing succeeded or failed, which is also 0 through 9. And then in a third step, you're going to need a third set of numbers, 0 through 9, for whether they live 5 years or not. So every patient here, so you're going to need a minimum of 30 numbers, and actually that might be too many, because if they don't survive surgery, then you really only need 1 number, not 3. So there you have it. Now that's the lecture. I believe that's everything that I'm going to say here. I'm sure I'm giving you some more. We've got 6 minutes. I can see, I could read my lips there. And then, so I was going to say, okay, we've got the rest of class, and you can do those simulations now. So now I'm sure I'm breaking you guys up into groups, but go ahead and do those simulations. Okay, I think I had one more question on about how to do this. So one way to do this, since we want 10 patients, and I'm going to need three numbers, is I could go down, starting say row 1, and I could use rows 1, 2, and 3, and each line would represent a different step for the patient, so you could do that. And then I would just need 10 across. So I will show you in the kind of screenshot and that you could do that as well. So I'm going to pause my thing here.